everyone, welcome back. So what we are doing today is design a web crawler. That's a fairly standard-ish system design question. Let's try to do it right, in a sense that let's first talk maybe for 5-10 minutes about the actual problem statement and what has to be done to solve it. And then
say again, Dima, sorry, I missed it. Like my headphone disabled for a second.
It's all right. So we're doing a web crawler. Let's do it right for now, and let's maybe dedicate the first 5-10 minutes to making sure we postulate the problem correctly. So what is web crawling about? What are the issues? How do you gauge success? Who wants to go first? I'm sure there are questions, as in, what are we doing? Any takers?
Maybe me. Okay. I think the major problem with the web crawler is that we have billions of pages to process. So yeah, there's a lot of work to do.
Mm.
And do we need to maybe index the data post the crawling phase, or else do we just need to dump the data somewhere?
Good points. So yeah, there are millions, probably billions of pages. Let's focus on crawling for now, as in imagine the indexing and the whatever we're doing with them later is being taken care of by some other team. So all we need to do is maintain the index. We have like a callback, which we do call on every new page crawled or updated, but we don't really care what that module does with those pages. We just need to make sure the pages are up to date. I have to confess, I didn't really know the size of the internet, so I looked it up. Yeah, it's tens of billions of pages. And it's probably like hundreds of petabytes to an exabyte of storage. So definitely more than one machine.
And are we thinking of like, so whole this hosting, whole this crawling is done by a botnet, as in like the computers which you have control, or else which you have minimal control, or you are a company who is crawling this?
Well, it's a good point. I mean, there are decentralized crawlers. That's really hard to build. Let's not go there. So imagine you are the company that is like early Google. I actually like to frame my interviews as in, imagine it's early 2000s or like late 90s. So you really want to build the early Google. You do have a couple computers in your garage, you have a prototype, you know it works, you know the product market fit is here. You just need to scale it.
I guess we could discuss a little bit about the features that that we want to implement or the requirements for the web crawler, right? And just kind of thinking out loud, right? We want to have like, we need to be able to parse links, right, through these web pages, right? So, I mean, to even get started, we need to have like a set of links, right, that will give us our starting point so that we can start crawling the web, right? So that's kind of the very first feature that we need is just being able to have a subset of links and then be able to parse all the links and then continue doing so in whichever manner you want to do it. Another feature perhaps, right, is validating, right, these links, right?
Mm-hmm.
So we want to make sure that to check whether or not some of these links are valid, right? And I guess another potential feature we want to do is like at the end is perhaps have like at least from Google, right? It caches when you search on the Google, when you're searching on Google for a particular page, it caches kind of some of the results. So I guess going back is the feature to have like purpose of this web crawler is to like have a UI that would like similar to Google in which you can search and have a set of results return,
Mm.
Or is it internal, just gathering, collecting indexes from these pages? And
Okay, so you made 3 points. The last one about whether we need to like build a UI for the actual search engine. Let's not go there. I mean, from the system design perspective, the crawler doesn't have to crawl the web for the purposes of indexing it. It can have any other purposes. I mean, you may be like looking for legal content with some fingerprint, in which case, all you need to do on the crawler component is to get the URL, I mean, get the data for the URL and send it somewhere. Whatever happens there is not your problem. So let's not worry about the UI part. The second thing you said about URL sanitization as invalidation, well, I mean, there are invalid URLs, but what can possibly go wrong? You just cannot crawl it, right? And the first part is yes, that's a very good point. In order to start crawling, we need what is called the seed set of URLs. Ideally, the web graph is connected, as in there are no disconnected parts or pieces. So in theory, if you just have a couple like high-level pages, you should be able to get anywhere. Like for example, if you have a link to Wikipedia, at least one. From any link to Wikipedia, you can get to any other link in Wikipedia, and then from there citations and references, you can get to pretty much anywhere, hopefully. Again, let's not go there. Let's really try to do it right. Let's first talk about the requirements per se, and then once we define the requirements, we talk about how do we solve the problem. So the actual, like, how do you sanitize URLs? How do you validate the URLs? Is like a second order part. Let's focus on the first order part first. What would we need to make it happen?
so what about in terms of, to just make sure I get the scope, like for the features part, right? We wanna gather these links, right? But sometimes there's, are we just gonna focus on like HTML pages, or are we gonna focus on like, because we could potentially have like other types of, different types of links with, different data.
That's a very good point. So in order to be able to crawl the web, we need to be able to extract links to follow further. Like these days with hypermedia and standards like this, you can argue that you can extract further links on different formats. But when we're talking about the original web crawler, like imagine the 90s or before the 90s, I think the only format, like mostly the way you would get other URLs would be from the HTML content themselves. So you would crawl a page, which is the HTML, you find other links there, and that's your further crawl set. But again, let's not go there too much because it's going to be a conversation about how do we solve the problem. Let's define the problem first. So you have the seed URLs. You need to crawl whatever you can reach from them, and you need to keep crawling that because the web changes, right? So some pages, well, most pages, you need to recrawl. Some pages like CNN top page, front page, you probably want to recrawl pretty often. Some of those you can just crawl once a month or so just to make sure they didn't change. And you can even keep the checksums to not update them if they didn't change. But again, we need to crawl everything and we need to store everything. What do we need for that? We had this argument about, do we own the machines? Well, we do. We control the data center. How do we actually get to the internet? How do we actually crawl? You can't crawl the internet from your own computer. That's a bad idea. What do you need?
I mean, we need servers, right?
Well, you need servers, not just servers. If I have a basement full of servers, it's still not fully equipped to do the crawling. My home internet won't handle that. My bandwidth would be an issue.
Yeah.
Well, also, yeah.
Bandwidth would be an issue, and the other person might think your request as spam, and then you need to adhere to the robot.txt maybe, and then. Yes.
Robots.txt is a big question. Yes, we'll get there. But yeah, it's a good point that other people may think I'm a spammer. I mean, a spammer as in malicious agent. In which case, they may refuse to send me their data because I'm crawling them from the same IP address and stuff like that. So we need multiple computers, or rather, we need the way to crawl data from multiple locations across the globe, right? So it's like a reverse CDN. For the CDN, you need to serve data from different locations. For crawling, you need to crawl data from different request origins. So let's say you have that. let's say you have multiple data centers, or at least multiple beefy servers if you're in the late 90s. You have them in America, you have them in Asia, you have them whatnot. What happens next?
Next thing in terms of like maybe storage and as in like compute, I meant CPU. So we just need to get a rough ballpark numbers on like how many pages are we gonna scan, and then are we gonna scan all the pages every day? So maybe initial, do we need to, so for each page, so can we assume there is, can we think of there is one another system which tells us like how frequent it might probabilistically it might be updated?
Yeah, it's a very good point that we don't really know how frequently we want to crawl it, right?
Mm-hmm. Yes.
Something you may want to crawl pretty often. Some things you don't need to crawl at all. I mean, you can crawl it once a month or even once a year. It's tricky because the answer to this question would depend on the actual user of your crawler. If it's a search engine, you would say, hey, whatever changes more frequently has to be, whatever changes more frequently, and whatever people are looking for more frequently has to be crawled more frequently. All in all, I don't think it's if we go there, it's going to be a longer conversation. So let's just say we want to make sure we crawl everything like once a month or so. Mm-hmm. And yes, I think it's a very good point that what we want to estimate first is how many pages per second do we want to crawl? How many crawls per second should happen? Usually, if it's a real interview, we would probably discuss what's the ballpark for this number. But for the purposes of saving time, let's say I throw out the number. Let's say it's like 5K per second, 5,000 crawls per second. Overall for the whole fleet. So for all your machines, for all the servers you control. Let's take it from here. How many crawls per second do you think a single server can do?
They like 100. Good, be conservative.
You actually are video-less.
I'm Hana, sorry.
It's just on my Zoom, because I'm recording, I'm hiding the participants, so you just disappeared. I can see you talking. I can see a message that says you're talking, but I cannot see you. So yeah, 100 per machine sounds reasonable. So 50 machines doing the crawling, I think it's a good estimate. Now, what else would we need to do besides the actual crawling part? Well, let me phrase it better. We know that 50 machines can crawl full time, and that's going to be enough for us. But can you do it really on 50 machines, like the whole crawler task? Or do you need more machines to handle the overhead?
So I think of it as a background task. There is no surge in number of URLs. So we have one thing we can do is, the major thing that comes into mind is, so whenever we are getting, if we get like 10,000 links from just one web page, we might need to serialize, maybe put them in a queue and then process one by one.
Right.
Other thing would be the idempotency of the URLs.
Idempotency, you mean uniqueness?
I meant like uniqueness. We shouldn't crawl one URL more than once. So in that particular session, so we don't go in loops.
True. Well, yeah. So loops are actually tricky because they can be different constructs that create artificial loops. There's even this term, I forgot the term, like crawler trap or stuff like that.
Okay.
And the server can generate more and more URLs, so the crawler runs forever. The server is malicious with respect to trapping the crawler. Let's not go there yet. Very good point. So we have multiple components. We have multiple jobs to perform. One is the actual crawling. That's most likely network bound. You can probably scan through pages and save them way faster than you can crawl them from the internet. The other one is this queue part, where you need to store the actual crawl queue. I think the third part you mentioned correctly is this, let's call it uniqueness. So it's like, for the purposes of simplicity, let's assume it's like a big hash map that we have, like that maps URL to like last crawl timestamp, for example. And then one part that is also essential is we need to scan the contents of each page, at least to extract what other URLs to crawl. So let's talk about this 4. I mean, this is not by far not a complete picture of the crawler, but it's more than enough to get started, and it's actually more than enough to cover any interview on system design. So I think we should focus the rest of the conversation on how these 4 jobs can be distributed across multiple machines, across multiple tasks. What gets parallelized? How do they talk to one another? How do you store the data? So let's pick one of them and start talking. We have 50 machines that do the crawling. Let's say they all talk to each other or through any queue, whatnot. We can discuss this later. Let's pick one of the remaining 3 tasks and focus on that. What's more interesting for you guys?
Dima, sorry, you said it's 3 tasks or 4 tasks? Can we please repeat them?
Crawling, the actual crawling, that's one. The queue that tells you what is there to crawl further. 2, the large hash map that knows what has been crawled and when, and the component that goes through each crawl page to extract more URLs to be added to the queue.
I see.
What we have not covered here is how do you store the URLs, but let's say you have a huge object store or whatnot. That's ironically the easiest part because distributed object stores that require no joins, just storage is kind of easy these days. I mean, people know how to do it. It's not hard. So the three things other than crawling are the queue, distributed hash map, and parsing the URLs, extracting the URLs. What do we do first?
Crawling and then the maybe patching part is more interesting.
Crawling as in?
Crawling as in like fetching the web page and then passing through the content and then inserting it back into the let's say the queue.
Okay.
Just the CPU and network bound operations.
What is CPU bound?
Crawling is CPU bound as in passing through the web page, reading through the web page, identifying the links.
Okay, let's maybe not use the word crawl because it could be confusing. It means different things. So there is like retrieval, network request and network response, and there is parsing. I'm just suggesting the terms. We can use any other terms. So the web retrieval part, I don't think it's CPU bound, to be honest. Network is asynchronous in most operating systems. Like for the simplest purposes, you can think it's a Linux box where you can run multiple curls, and it just crawls them for you in the background. You will do a lot better in practice with event-based network card utilization. But crawling itself is kind of straightforward.
Question. I mean, one thing, if let's go with the case scenario that I have a list of URLs, my seed, right? If we talk about the crawler component, right, then one of the things that happens when you fetch there's a lot of things that happens when you fetch a website, for example, DNS resolution, right? So that is extra network calls potentially that can be put in a different component of the system design or architecture, so that the fetching of the page itself, the crawling that's going and getting the page, right? All it does is directly gets the page, right? And that itself, it's kind of its own, I guess, potentially service, right? And once that page is received, right, and there's a parsing aspect of it, which I think is, somebody mentioned that's very CPU bound, and perhaps that could be pushed into its own service as well. So for the crawling, I think there's like three parts, right? One of them is just resolving the DNS. Another one is fetching it, right? Another one is parsing it, which could all be done, in different services themselves.
Yeah, we will talk about how to separate the work between getting the page and parsing it in a minute. But you actually mentioned DNS resolution, which was not brought up before, and it's an important point. Does everybody know why is it so important? Like, what if you ignore the DNS issue altogether? What would happen? What if you just crawl each page afresh, as if nothing happened before? Well, what would happen is that let's say you crawl using curl, the Linux command. You type curl space the URL. What would happen is that the first thing it does, it has to resolve the name of this domain to the IP address. We would open the socket and then start requesting that data. Assuming no malicious intent, assuming no service that will try to give you different IP addresses for different requests, it's just a round trip. It's an extra call to make. At the same time, if you're crawling, let's say from New York, from a data center in New York, there's a good chance that the IP address to which certain URL, certain domain maps would not change. So if you cache that, if you want to crawl 1,000 pages from NewYorkTimes.com, you can only run the DNS query once. So you save a lot of queries. So there's some idea, there's some truth in the idea that you can cache the DNS response. Now, whether you cache it in some other external cache shared by all the machines, or at least all the machines you have in certain location, or whether you cache it per machine because you don't have that many crawlers, that's a separate conversation. But all in all, yes, at least per machine, per single crawling server, you want to keep some cache of DNS requests so that if you need to crawl a new page from nytimes.com, if you did crawl something from that domain, you don't need to redo the lookup in the DNS tables to relearn its IP address. That's a good point. Thanks, Andy. Now, the actual crawling, as in getting the contents from the web, and page parsing to extract other URLs. There are different strategies. You can put them onto the same machine, or you can put them onto different machines. You can do more fancy things, by the way. Intuitively, what do you think is a better solution?
Well, what do you mean the actual, I guess I'm not really clear on what you mean by the actual crawling and fetching of the page get put in the same machine or a different machine. Are you saying that, we know that we need 500 machines, right, to be able to scale 5,000 requests per second, right?
Correction. Correction. We need 500 machines.
Oh, sorry, yeah.
To use the network.
Right. So you're asking, should this crawling be done at distributed? Is what you're asking?
Well, we know it is distributed.
Right.
We need to orchestrate 500 machines.
Right. So I guess I'm not really clear on your question, right? Of one machine versus multiple machines.
So let's consider one of the machines that does the crawling, one of 500. It is busy all the time because it keeps requesting more and more pages from the internet and getting their contents through its network card.
Mm-hmm.
Let's first of all figure out it most certainly is busy 100% in terms of network bandwidth. Mm-hmm. How busy is its CPU? Can it do other things?
Yes.
Is it Bargov has something to say?
No, go ahead. I was thinking in that of yes. This is mainly network bound. We can use the same resources for parsing the pages as well.
Yep, I think so too. So we can use its CPU for something else. For what exactly we can talk later, but its CPU is available to be used. Now, so imagine this machine is crawling, as in fetching the contents of 100 pages per second. You have some CPU intensive task, which is to parse the contents of the pages to find other URLs. How many per second do you think it can process? In terms of CPU?
It depends.
Kane?
I'm saying it depends.
I Are you comfortable sharing your video? You will be a bit more, yeah. So it depends is a good answer. Why?
There are multiple factors. Like you cannot predict how many you can crawl per second because you don't know how fast they respond.
Well, it's a law of large numbers. The pages can be of arbitrary sizes and they can be on slow and fast servers, but on average, the average is a plausible approximation, right?
Well, you'll have to find out the average then. Like you have to know your average, let's say like response speed, you have to know the average page size, and from that you will have to figure it out. But right now I will not dare to say what the number is.
Okay,
can we assume the page size could be something like 500 kilobytes?
Then we can do some math based on that, yeah. But better if we do test and we know like in practice how much that will be. Like I would do a test.
You would? Sorry, I didn't catch it.
Well, I would just do a test, like a benchmark, a load to see how much the, like particular my machine and my data center can handle.
Yeah. Well, that's the answer of an experienced engineer. Whenever in doubt, measure in practice. It's always a good advice. In fact, the stronger the team is, I work with different teams. The stronger the team is, the more open everyone is to running experiments. It's oftentimes a good experience just dedicate like a week to build some test setup just to make sure our guesses about the real world are correct. So we need 100 machines to crawl. We need to parse those pages. Depending on how expensive the parsing is, we may or may not need more machines. So as Kane is saying, I mean, as Kane and Andy are saying, if your pages are relatively small, like 500 kilobytes, then there's a good chance the same machine can parse all of them. I mean, the same machine that is doing 100 crawls per second, the same one machine out of 500 can also afford to scan all these 500 pages and extract all further URLs from them. Let's assume it's true. I believe it is. It doesn't have to be the case, but let's assume it's true. Oh, we'll get there in a minute. But the more tricky part is, once you have those URLs, you need to insert them into the crawl queue. How do you handle this? Where does the crawl queue even live?
Well, you know, if we want to make it a little bit more fault tolerant, right? Q could be its own server, right? So that we can each I guess process that is parsing this URLs could add it to the same queue, and then have other processes read from it.
Agree. Now the question is, how do you make sure this queue exists?
How do I make sure this queue exists? That's I guess I don't understand that question.
You'll need some way to have a queue that access from all the machines. And as you said, for fault tolerance purposes, you want to make sure that it's not localized on any single machine.
Right.
If the machine dies, or what if the network to that machine dies? So you'll need some well, let's take a step up. Let's take a step up in terms of system design. The way it's usually done, especially in interview settings, is you try to break down the system into components. Because the easier each component is to explain, the easier it is to develop. Like imagine you're a super senior engineer. Imagine all of us are super senior engineers. And we're the architects here. So people who would be implementing on our design are less experienced. So we can take shortcuts because we know how to handle this. They don't. So we need to explain them in the simplest words possible so that once we're gone and they end up working on our design, they don't screw things up. So for that to happen, we need to explain them in the simplest possible way, what's going on. That's why we have this component that crawls the web page. Done. Component that parses this page. We are suggesting that this component runs on the same machine that crawls the page. Good. Now we're saying, hey, there's a queue. And this queue is distributed. And this distributed queue must be fault tolerant. And all machines have access to it. And then like if at this point you say, hey, that's what I'm suggesting, and you leave, those guys would be really confused. What are you even talking about? How do we make it happen? So what exactly do we mean? We have to go deeper here. What exactly do we mean by we have a distributed fault-tolerant queue. What's the API to that? How do you implement that? How do you make sure it is actually fault-tolerant? Let's talk about this. Oh, actually, Sergey, you were first on my random list. Maybe you can take it from here.
Yeah, okay. If we want our queue to be fault tolerant, it should be a persistent queue. Otherwise, if any of the machines fails, we would lose some important data, namely URLs. That's the first thing. It should be persistent.
Maybe you can tell us more about what does persistent queue mean?
Well, when an URL is added to a queue, it is saved on hard disk, not just saved in memory. Well, another important thing that we can actually lose this machine and the disk itself for some unexpected reason. So this queue, there should be like a replication of data in this queue. So if any of the machines fails, there is another machine which can serve our requests for URLs. So yeah, those are two things which come to my mind first.
So persistent means everything that's added to the queue is stored on a hard disk?
Yeah.
And it's stored on more than one hard disk, just in case one of the machine dies. One of the machines dies.
Yeah.
Okay. By the way, do you have any preferences as to which queue to use? Like any open solutions so far, or would you build it from scratch?
Well, I would. I'm not sure if Kafka was available at the time when we are building this. Okay. So we would have to build it from scratch.
Kafka is actually a good suggestion here. And since you're familiar with the name, maybe you can tell us more about what it does.
Well, what's special about this software is that you can insert records into it really fast and extract it from it really fast, one by one, like a queue. It's not like a database where you can get any record by some key. It's just like a queue, first in, first out queue. Yeah, so its functionality is pretty limited, which enables us to this speed, to have this high speed of insertions into this queue. Okay.
Is everybody following, by the way? Is everybody following? Everything Sergey is saying makes sense to me. So I think we should really tell people more about what message queues are.
In this example, I'm that unexperienced engineer. I've never done this messaging queue, and mostly I work locally. So I know there is Kafka, but even the question like how much is fault tolerant is kind of like puzzles me. Okay, I can just like have a whatever daemon which has like 7 like data queues handles and just like send it with some indexing like over and over. And like if one isn't available, it throws away and just send it to like others, and so on. So the whole point of like fault tolerance, I think, is kind of built in the question or maybe in the answer. Or is it about the product? Okay, this product is fault tolerant. It does this. Think about the like demoning and like queuing and selecting between available connections or something like that.
Well, he who asks the right question knows how the answer. You postulated the right questions. Let's talk about what should the API for the queue like Kafka be. Sergey, would you like to take it?
Yes. So the API, there should be like insert operation, which inserts a message into the queue, and pop operation, and it's pretty much it. We think we need anything else here. Yes,
At
and
this point,
this insert operation and pop operation. Yeah.
at this point,
Sorry, my internet.
You were breaking up. I'm not sure if it's your connection or mine. Anyways, at this point, most interviewers would ask something like this, and I think Anton would ask it as well. So you need some magic black box to which you can push records and you can pop records from there. Can't you just use a Postgres database and write a transaction that adds a record into a single table with a key being the timestamp and the value being your value, and then implement the getter, which just selects the least recently added record or a few of those? And we got to be able to answer this question. So what's the need for Kafka compared to Postgres?
Okay, the first thing is, because if we insert something if we use an SQL database as a message queue, we could suffer from its speed, actually. And the next thing, I guess, is locking mechanisms, because with a queue, I haven't worked with Kafka so close, but I think there is a possibility to pop a message from the queue and to somehow signal to the queue that the message is processed. It can be deleted from the queue. If we use Postgres, we would have to implement this logic by ourselves, and there would be a distributed locking mechanism, and it's not straightforward how to implement it.
Okay, let's talk.
I would like to stop here, sorry, Dima, and add some notes to what you said, Sergey. The biggest difference why Kafka became so successful, and it was different from the existing queues, is that it's not really like a message queue. It's a distributed transaction log. And the biggest limitation that it puts on you, that you cannot act messages out of order. So there's no acking mechanism. There's really no getting message and acking it. What you do, it's a transaction log, and you have to remember which offset in transaction log you were on. And that's why Kafka design is genius and simple in its way, because it is very simple. It's just a continuous file on disk, and you just remember literally a file of set, and it just distributes this file over replicas, what they call it, replicas. And the design is so simple, Kafka doesn't have to do much on their side, whereas Rabbit has to do much more, Rabbit and Q, for example. But the API is completely different. There is no get message and act message in Kafka. You stream messages and you commit the offset. That's the difference.
Oh, well, yes.
I have a question.
You're off camera again, by the way.
Oh, sorry about that. Yeah. So I guess my question is, something that Kafka sounds like a great technology, right? And it has a lot of great features. And one of the I think best features of Kafka is that you can do things in parallel, right? You could have multiple things pulling. And I find that that's kind of how I use Kafka in the past, where I have multiple consumers consuming the data. But in terms of this problem that we have with that, we have this particular I guess we're building this web crawlers where we don't need. It sounds at this point that we don't need kind of to read parallel, in parallel different consumers, right? Why is it? Wouldn't something like Redis, a much more simpler technology, could be used to, which is also distributed, could be used to solve our problem?
Did you say Redis?
That's correct. They also have is that in-memory cache that can also be used as a message queue.
So yes, it's a good question. We should talk about this. Let me make a small detour here, just in case we're not all on the same page. So when it comes to, it still says Andy is talking. All right, never mind. It's just I have this blue thingy. So there's a few things to unpack here. One is that there are message brokers and message queues. And I think it is accurate to say these days that historically brokers are by design about routing and queues are about persistence. So oftentimes what you end up using is not the message queue, but the message broker, which is like different topics, different routing rules. The same message can be delivered. The same message can be delivered to multiple, like fan out to multiple different destinations. If one of them dies, no big deal or whatnot. And there's no guaranteed at most once delivery. It's just a means to like it's a huge forum where you can send a message which is broadcasted and something happens. And this is not what Kafka is. This is what Rabbit is. This is what AMBQ protocol is about. A lot of tools, a lot of techniques, a lot of systems can be built based on this idea. Kafka is the opposite. Kafka was actually designed to power database to database replication. Imagine you have a database with like petabytes of data and you have leader to follower replication. Like you need to move from data center A to data center B. It's a huge pain. And before Kafka even existed, you had to power down one data center more or less. Like have a planned downtime to move the data, maybe physically copy hard drives, and then the DBAs would resume the database in a new data center, hoping it works. Kafka was designed for this particular purpose, to make sure you can synchronize the databases so that you have the leader database in a certain data center and the live replica, which you can use as a hot backup, and then you can flip them. So like you can decommission this data center with a small window of immutability, because with this small window, you only need to send those last few seconds of data that was not yet replicated here, and then you fully back live to a new data center. So in order to guarantee this reproducibility, Kafka had to store the data. Kafka had to be persistent, and Kafka is designed this way. So there's a queue, as Kane says, there's a queue of messages. Each gets its own unique index, not even the ID, the index, and it stores them sequentially, and you can replay them sequentially. Kafka is doing some magic with respect to what to store in memory, what to store on disk, and what to cache and when. So to you, it's just an infinite pipe where it has a guarantee that if you subscribe to a certain queue, it's not really one queue, it's multiple topics that are kind of independent. But for now, you can think of one queue. If you have this one queue, every single time you put something there, it gets added. It has a timestamp and the index or offset ID, pretty much starting with 1 and going like the number of records added so far from the beginning of the universe to this particular pipe, this particular queue. When you want to get data from this queue, what you do is you say, hey, I'm a getter, and I would like to get messages from index 1,573,000,000, and it begins streaming you the rest of the data. And you can have this guarantee that within a single queue, within a single topic, the indexes will be respected. This is a really good abstraction if your single pipe, your single queue has enough capacity. When you have a lot more data, it's your job and it's your headache to make sure you split the data into multiple queues that can be off in their indexes and their orders can be messed up or whatnot. That's tricky. Let's not go there. When it comes to crawling, Kane is right, but we didn't cover the most important part. We have more than one crawling machine. We have 500 crawling machines. And Kafka does not solve the problem of which machine gets to crawl what. So we have 500 machines that do crawl the data. Each of them gets to parse the URLs. Each of them extracts other URLs to be added to the queue. We have not really talked about the component that deduplicates the URLs, but imagine it exists. Imagine we have it so far. So every single URL goes there because it's possible that we'll just scroll 2 different pages and there's the same URL on 2 pages. You only want to add it to the queue once. I mean, you want to make sure you don't crawl it twice. So either add as you add it to the queue or as you extract it from the queue, you need to make sure it's not duplicate. Forget this for now. Let's say it's all in singular. You add the URL to the queue. The queue is never empty. Hopefully the queue always has URLs to crawl. It's actually pretty large. And then you have this 100 machines, 500 machines doing the crawling. In theory, if you use Kafka as the data queue, as a message queue, as a data bus, each machine can just ask, hey, I'm at offset something, I'm at index something. Give me the next 1K URLs. In practice, the machines must somehow align on which machine crawls which URLs. And that's a major part of the problem. Am I outlining the problem more or less clearly?
Yep. Yeah. In the beginning I thought that there could be some partitions in Kafka queue, like there are some partitions, and in each of them there is a pointer to an index, like the current index, which is processed. But I don't know how to connect those partitions with all the machines we have for crawling, like how to assign machines to partitions. And yeah, it seems like with Kafka it doesn't work.
Well, given Kane is here, I think you wanted to say something.
Well, just want to like stop a little bit with Kafka. I think like it is possible to do Kafka. Just requires a lot of creativity. I tried something similar once. Just want to outline the problems you will encounter. You write like in Kafka, topic can have multiple partitions, and partition is the unit of parallelism, what it's called. The problem though, like let's say like the way it's getting distributed is usually a worker takes ownership over the partition. That means like that is to guarantee the sequentiality of processing, because there's only one offset you can commit. Obviously, like you cannot have multiple workers working on the same partition, because there's only one commit you can do. Like there's only one offset to remember. So to do the work once, you should like have one worker per one partition. So the problem with that is you apparently like need potentially like many thousands of threads working on, say like fetching their URLs. But Kafka partition is limited. So, and that stems from the Zookeeper's limitation that it's using behind the scenes. Zookeeper, I think like has a hard limitation of 5,000 nodes in a tree. So that's about, even like before that, like way before that, it becomes slow, like about like around 1,000 partitions, it becomes slow. So you will be like pretty like hard bound to 1,000 threads. And that's not like how you can do that. So that means you will probably have to assign less, have less partitions, have less working threads, which will be like kind of like a more like fan outs, which will grab chunk of work, fan it out to the like sub pool of threads that do actual work. And then like when the work is done, they commit the whole chunk to the partition. That's kind of the pattern of how you work with Kafka. But in our case, the problem is you take the, say like you take the chunk of like 100 entries and you have 100 working threads. And let's say like 99 threads finished very quickly, but one thread is slow loading. It takes minutes to respond. When we have to wait until that last person like to do the work, because you cannot commit, like you cannot continue work while like this one is hanging. Like you like literally cannot persist what you were doing. And that is a problem. It is possible to solve, but it will be much more discussion around this point here.
Well, yeah, let's unpack this. You said a couple of things that I think absolutely everybody should be aware of. So first of all, let's keep the Kafka internals part out of conversation. We have a topic, and the topic has partitions. Each partition is independent. That's just Kafka internals. It doesn't have to be this way. It just turned out to be a good design for a practical solution, and it's stuck. So we'll live with it. So you can have a topic. You can have a single queue, but ultimately each single partition is like a fiber within this topic. Within Kafka, one fiber would have its own offset. And what Kane said about committing is that you can always request data from certain offset from a given partition of a given topic. You could always say, hey, from topic URLs to crawl, partition 26, I would like to get data from index 1,017,000. That's perfectly fine, but Kafka actually lets you commit the index you have processed. So you can say, hey, you know what? Up to index 1,017,000, I'm done. I've taken care of it. So the next time you just request the data, and Kafka remembers from which do you need this more data, which is an awesome idea, except if two workers are operating the same partition, they would reuse the same commit. They would reuse the same index. They would both move the same handle, which is a bad idea. So for simplicity, let's just assume we keep one partition per topic. In our case, we can just say, you know what, like all topics are independent. We actually did talk about DNS resolution. So we can always say, you know what, I'm going to have 100 topics or even 10,000 topics. I'm going to take the URL. I'm going to take the domain of the URL, so the domain name, not the full URL, but just the domain. I'm going to take its hash, and I'm going to shard. I'm going to decide which topic it goes to in Kafka based on this hash module or something. I can have as many topics as I want. That's not the best design ever. It's just the easiest to explain design. So I can have as many topics as I want, in which case I can say I want to have one partition per topic. In this case, I can rely on Kafka keeping track of my offset. But then again, as Kane said, if you need multiple crawlers operate on more than one Kafka topic, you would need some software module, some orchestrator, some manager, which would do this job of assigning crawl tasks, individual crawl tasks to individual crawling machines. So you would say something like, you know what, you have these 500 crawling machines, and maybe every 10 machines, so 50 total, I have these modules that actually talk to Kafka. What this module does, it requests the next 10,000 URLs. It orchestrates work within this cluster of 10 machines. And once all of those URLs are crawled, it reports back to Kafka saying, you know what, I'm done here, give me the next portion. And then, of course, if one of these 10 machines dies, or, which is more likely, if one of these 10,000 URLs takes too long to crawl and stuff like that, it is a job of the orchestrator to still move forward. Maybe it just re-adds this URL to the queue again. Maybe it requests a new batch, commits the old one, but it remembers by itself that of this 10K URLs, this 3 must be recrawled. But it doesn't. It takes this job off Kafka, and it does it all by itself. Everybody following so far? And the Zookeeper part, honestly, that's a lot trickier. Zookeeper is the log file system. I mean, there are multiple ways to explain Zookeeper. And if you don't want to know what Zookeeper is, read up on what console is, because console is like the new Zookeeper, more or less. There are different ways to talk about what it does. There are at least 3 ways to describe what it does. All 3 are correct. All 3 give you different perspectives. I like to explain what console Zookeeper is as it's the best possible minimalistic extension of the idea of raft-based leader elections. So if you have multiple machines, you need them to maintain a single state. They need to all agree on something. It's always tricky to find the best way to start this conversation. But it's a good thing we have many of us, so I can read your faces and come up with the way that explains the most of you, all of you ideally. So imagine you need some consistent state across multiple machines. Traditionally, you would use an odd number of machines, like 5 or 7, because if it's an odd number, they can disagree like 3 and 3 or 4 and 4. So let's say you have 11 machines to agree. And you want a fault-tolerant system so that if one of the machines dies, the state is still maintained. This is called distributed consensus. It's a super hard problem by itself. It's one of those few things I would never, ever even consider coding myself, even though I'm a pretty good coder. I would say, you know what, I'm going to use something off the shelf because it's really hard. The protocols for doing that, the mathematical solutions, one of them is called Paxos. It's tricky, it's hard, don't go there. The modern one is called Raft. Again, it's tricky, but the idea is that internally, as the user of this system, you just talk to it as if it's one machine. Between themselves, they somehow agree on how to guarantee that what they expose outside is a consistent single state. Internally, they will have a leader. They have this notion of one of the servers is currently the head of the pack. And internally, they have the mechanisms to move this leader repeatedly. And more importantly, if the current leader dies or becomes unavailable, the others would hold a new re-election and agree collectively on which other machine is the leader. And they guarantee that once you make a request to update the state of this fleet, of this system, it only gets back to you with a confirmation once it's updated on the majority of machines. So that something should go really wrong, like more than half of the machines should go down at once, so that the state cannot be reconstructed. That's why it's slow. But in practice, in practice, you can think of it as a slow but reliable database. You can think of it as a small key value store. You can have like 100 keys and you can update values and it guarantees consistency. You would never ever want to use this as a database because it's super slow and ineffective. But you use it as this guaranteed consistency storage, mostly of the data of which other machines are up to date. Because if you need to orchestrate a cluster of 10,000 machines, you can do a lot if you have some reliable way to tell which of the machines are currently up and running, which of the machines are currently powering down, which of the machines are out of memory, and you need to rebalance tasks between those. That's how Zookeeper, well, not really Zookeeper, but its predecessor appeared. So one way to look at it is it's a slow but guaranteed to be consistent database. Another way to look at it is database just means some key value store or whatnot. Another way to look at it is to think it's a file system. That's why it's called a log file system. It's a remote file system which is slow, but you can like update files there, and other modules can read contents of each file or subscribe to updates of that file. You can say, you know what? There's a text file in the directory machine status. There is a text file like machine name.txt, and I want to know when this machine is up and down. So I subscribe to the file, and whenever this machine is up and down, I get the notification that it's up or down. So another way to look at it is it's a distributed queue of events, because you can think of it can be like a single file with updates, and you can always map this list of updates to the contents of the whole file system if it's a small file system, or vice versa. So you can think of it as like a single unified place where you track world's events, where the world could be like your data center or your fleet status or your Kafka fleet status. In this case, which Kafka machines are up and running, which Kafka machines are currently active with respect to their own hard drives, contents, and stuff like that. Okay, this was a lot. But basically, the idea is that because Kafka internally uses Zookeeper, or it could use console or whatnot, internally, Kafka has some way for all its machines to orchestrate this information about its own state within itself. So it's like an abstraction over the log file system. Then every single write to every single hard drive of Kafka instances doesn't really have to synchronize with everyone else. But because every single Kafka instance reports up to the Zookeeper log file system what it does and what its current status is, you can rely on Kafka to make sure that if certain topic is stored on like 5 hard drives on 5 machines, if one of them dies, Kafka would know internally through Zookeeper which ones are still alive. It will rebalance the data. It will make sure it copies it over. Once a new machine comes up, it would know from the Zookeeper cluster which other machines have this data. It will happen behind the scenes. The downside of this, as Kane says, is that if you have a single topic with 5K partitions or 10K, in terms of this log file system, in terms of how Zookeeper works, it would create, imagine files. They would really be files. It would create files, one per partition. And because this log file system is super slow, it uses Raft, or in case of Kafka, in case of Zookeeper, it uses Paxos behind the scenes. Because that's slow, if you have multiple partitions, like 5,000 partitions per topic, updating commit index per partition would be slow operation. So if you had the web crawler and every single crawling machine or every single orchestrator of the crawling machine updates its own commit offset, how far along the queue it is. If it updates it like multiple times per second, your log file system to guarantee consistency would be the bottleneck, which is expensive. I hope it wasn't too hard. So the idea is we have some queue. You absolutely want to shard it. Most likely you would shard it by the hash of the domain name, which is also good because you can save on DNS queries. Another important consideration here is that you probably want to crawl sites or pages from the region where they are hosted. Like if your web crawler is probably worldwide, you don't want to crawl sites from Singapore, from New York. You want your Asian data center to go to Singapore. You want your East Coast data center to go to East Coast, Amsterdam go to Europe, and Oregon go to California. So you can handle this on this partition or on this topic level or topic partition level or whatnot. Then you want not too many commits to your offset updates, because otherwise your orchestration engine based on the log file system, based on leader elections, will be the bottleneck. So you probably, again as Kane said, you would probably want to have some orchestrators on the lower level. So it's not the queue itself; it's the lower level orchestrators. They would distribute job to the actual crawlers. And then the actual crawlers would go to some other component, which does URL deduplication, which respects URL recrawl time. And this guy actually adds data back to the queue. And when it adds to the queue, like it's the only part responsible for making sure it knows which partition of which topic to write. Kane, did I somehow communicate ideas correctly?
Yeah, I mean, like that was a long, it's like a side talk, but yeah, it was right. I would like to go back and like talk more about like the design itself and like how we can design the system in this case. Like today, like at first. Okay, go ahead.
So, you know, during a design interview, system design interview question, right? I would like to like summarize, you know, why I made the decision of using Kafka versus, you know, another technology, say Redis or RabbitMQ, right? Because you know, I felt like we dove into like, you know, details of how Kafka worked, right? And I'm not sure, like from my experience, like I oftentimes don't get in. From my experience, from my interviews that I've had, I haven't had like someone ask me to go into the details of like Kafka, right? Oftentimes they ask me like, why did you choose this particular message queue, and what problem is solving for you in this particular case? And I would love to go back into just making sure that I understand what problem that you know, picking Kafka solve for us.
I think it's a very good question, and we actually have to compare three. We need to compare Kafka as a persistent message queue. We need to compare it to Redis, which is a different beast, and to Rabbit, which is a different beast. And I think Redis alone deserves quite some attention. Anybody experienced in Redis here?
I mean, I've used Redis before as a task.
You're off video again.
Oh, sorry. Yeah, so I've used Redis, right? And in the beginning, we talked about that, you know, can we go back to the requirements, which was about, we handled about 100 requests per machine. And then, you know, we got about 500 machines processing this, right? What was the total number of, it was 50,000 requests per second, is that right?
I think it was 5,000.
5,000 requests per second, right? Which is very little, right?
Well, little is relative. It's extremely low for Redis. It's actually pretty high for Zookeeper, for the record. And it's relatively low for Kafka.
Yeah, let's
take a step back. Let's take a step back. You are asking a good question. Let's take a step back. Anyone can tell us what Redis is good for?
In-memory hash maps. Distributed hash map.
Redis started as an in-memory collection of data structures, period. It used to be in-memory first. Like the number one requirement was in-memory. Number two was super fast. The number three was single machine. Redis, to the best of my knowledge, only recently Redis supports multi-machine replication in a way that you can trust. So, I mean, I would honestly not recommend relying on Redis as the data storage. It's a super fast hash map. It's a super fast queue. It actually supports different data structures. And we should really go even higher, I think. Imagine you want to wrap a bunch of data structures into a small service that would hold a lot of transactions per second because those data structures are all in memory. In fact, it's all in a single thread. Redis is single threaded by design. That's what makes it so fast. And that's why it's not using all the machines' power, because most machines these days are multiple CPUs, multiple cores. But if you want to guarantee it, no collisions, single threaded collection of data structures, Redis has it. I think the first one was the hash map per se. It's the HSET data structure. So imagine this service with with an API of two calls: add or replace key value. Deletion is part of edit. Remove the key. So add key value and get by the key. That's it. That's 90% of the original Redis use cases. Redis also has different data structures. Redis has lists and queues, which is important. For example, in Redis, you can say, hey, you don't really define data structures, by the way. It's all like loosely typed. The data record has a type, but this type is not tied to anything. You can say, hey, I have this hash map, and also have the queue. And you can add elements to the queue, front and back. You can remove them front and back, and you can atomically move them from QA to QB. And Redis, because it's single threaded, it guarantees that the move will be atomic. It has more data structures. It has priority queues implemented as skip lists. So you can have a data structure where each key has value and like score, and it gives you the possibility to extract the top score or like 100th score. So imagine you want to build a top 100 scoreboard for a huge multiplayer game. Redis is awesome for that. You don't need to do anything algorithmically. You just use this data structure from Redis, which is the priority queue. Yes, this is all good. Now you could use Redis's queue for our purposes.
Right.
But if the machine dies, it's gone. And in theory, in our case, the queue will be large. And obviously, at some point, your queue would explode in size. It would be terabytes, literally. Numbers of URLs, like huge list of URLs that are to be crawled. Like, think about it. When you just start your crawler from a small set of seed pages, each of them adds, well, I would say 50 more pages on average to be crawled. And when you're just starting, there's no intersection whatsoever. So it's a huge exponential growth. At some point, you'll begin hitting duplicates because you'll begin trying to add links, add URLs to crawl, which have been crawled before, or at least already are on the queue. In which case, your queue size would slowly start decreasing. But you'll have to keep a huge queue, and it would absolutely never ever fit in memory. So in which case, Redis is a bad choice here. Is it clear to everyone? Or was I talking too much again?
So when Redis is distributed, right?
No, I honestly think it's a wrong way to think about it. Redis is distributed these days, more or less. But since it's not its original purpose, I would not rely on it yet. Redis supports some distribution, some leader-follower replication, and some hot backup functionality. Honestly, I don't think it's mature enough right now.
Okay, so another question is then, I mean, I love talking about Kafka is great, but to go back to
Andy, you want to turn your pen back on?
Oh, sorry about that. So I guess Kafka is a relative new technology as well, right? When Google was created, right? I'm sure Kafka didn't exist then. So, so my question is, what if we weren't thinking in terms of Kafka as like our technology that we use, then what kind of alternative would there be to solve this problem?
This is a very good point. Like, it's really interesting. You're asking all these questions, and you try to sound naive, but you're asking all the right questions because that's exactly how you should think. Kafka did not exist absolutely. Kafka actually was first built as a site internal project in LinkedIn, I believe, in around 2005 or so. So yeah, clearly when Google was just starting, Kafka was not there. But the idea of Kafka is the same as if you keep appending lines to a text file, and you can read this text file later. So what certainly existed when Google started is distributed file systems, like as in low number of machines distributed, RAIDs. Do you guys know what RAID is?
I'm not familiar with RAID.
You can configure hard disk to be different RAIDs, RAID 1, RAID 5, RAID 10, so for different replications.
Right. So if you want a reliable storage, oftentimes you do need a reliable storage. And it's a question of whether you solve it on a database level, on a cloud database level, or on some lower level. And before clouds existed, before Oracle claimed that they can store the data securely, RAIDs were there. And RAID is just a file system. You pretty much, it's like a physical thingy where you put multiple hard drives, and there is some device driver software plus hardware that makes sure that once you write a file, it's been written to multiple hard drives simultaneously. I don't think it's file-based. I think it's block-based, honestly. I'm no expert here. But the idea is you can rely on this data being stored reliably, and you can if it's like 5 hard drives that store the data, you can swap one of them with a new one because the hard drives used to slowly begin having bad blocks and stuff like that, and the data would still be available. So I think when Google started, I'm just speculating again, even though I was at Google back then. When Google started, I would argue that what you could do is the following. What we call topics here, we could shard them. Remember we talked about sharding URLs to be crawled by their domain name. Then you can hash the domain name. You can come up like with the first few digits of the hash and have n topics. So if I would be building Google today, what I would do is I would have a RAID cluster, and I would put some file system there that is comfortable with having multiple files, a lot of files. I think back then it was ZFS, like Razor and ZFS. And I would say, hey, you know what? I have a bunch of directories, one per topic. For each directory, I'm going to have a bunch of files. And the file is like today's year, month, date, and maybe hour. And in order to add new files to be crawled, I just append to this file. I just write one URL per line. It's a super simple to understand analogy, right? And then the machine that is responsible for reading this file, there should be only one. Because if multiple machines are reading the file, they would conflict on what to be crawled. But if there's just one machine that orchestrates crawl tasks from this file, it would know up to how, if this is the file for the current hour, it's being appended to from the bottom, and the machine that reads it is reading it from the top. And all the rows, all the lines from this file it has read are currently being processed by this small subcluster orchestrated by this machine. And then clearly, like files are being added, let's say 1 per hour. I'm just making this up. And then the reader just goes through one file and comes to the next file, and that's it. That's pretty much the logic that Kafka would abstract away for you these days. All Kafka does is replaces text files by topics and RAIDs by Zookeeper orchestrated classes of machines. It does a lot more, but the idea is that if you have your own hardware and you want to optimize it like to this level, what I'm telling you about RAIDs is probably a good enough solution. But if you would try to do it these days in a startup, it would be laughed away because that's just not how we do it. Even though it's probably cheaper in terms of maintenance, it's just more advanced. You would say, hey, use Kafka, and the good reason to use Kafka is of course because it supports high-level abstractions. You don't need them for web crawler today. You would do just fine with text files so far. But later on, you would need to sub-shard the topics. You need to subscribe to parts of data. You would need to filter it at the receiver level, at the message queue level. That all these things are possible out of the box or with small fine-tuning with Kafka. Now, I mean, honestly, I do believe we should thank Andy for this question because it's important. So Kafka can be workable if you have your own orchestrators. Text files on RAID clusters can be workable too, although it's like 90s solution. Google started in 1998, so it's still 2000s. The third thing we had to talk about is rabbiting queue. And that's the difference between message queues and message brokers. Message brokers, again, their main difference is that they are not persistent. They're not designed to guarantee the data will be there. Keep in mind, Kafka was, like honestly, when I was in this business, I actually built my own stuff of this capacity. And I was surprised how it's as if it's a multidimensional space. You need persistence, you need replayability, you need multi-machines for partitioning purposes, you need some logic on how to subscribe to parts of data, at least once guarantees. And this space is very loosely covered by different solutions that take this, they claim that some part of this multidimensional space is important. So Kafka says, you know what, I'm replayable, I'm persistent, I guarantee the order. And Rabbit says, you know what, I can fan out data, and it's all going to be in memory, and you can define these fan out policies in a very nice language, and I'm going to do it in a super effective way. But again, if it dies, it's dead, you lose the data. So it's important to understand that they're not complements of one another. They're just different solutions that optimize for different tasks. So again, if you just need to add once, process once, and do it in a reliable fashion, that if everything dies, if your data center is fully powered off, never happens, but still, your hard drives would still have the data, forget Rabbit right away. Redis could be okay because it still stores stuff on disk, but that's pretty much what Kafka was built for. If you need to orchestrate multiple listeners, multiple subscribers, so if your inbound flow of tasks is something you can possibly lose, they are ephemeral. If it's gone, it's not gone forever. It's going to be retransmitted from the emitter of this event. But it's important to make sure that the events propagate to different workers according to different rules. That's what Rabbit does for you. That's what the AMPQ protocol does for you. That's a different piece. It's a tricky part. It's optimized for different things. It would copy pointers in memory to send the data to different places with no overhead, with no copy, no extra copies, no redundant copies. That's painful, but it's a different problem. Was it making sense so far?
Yeah, that's very good, excellent explanation. I really appreciate that answer. Oh, sorry, excellent explanation. Yeah. Thank you.
I mean, honestly, I think it's really good that you asked this. It's really good that you asked this because in the context of preparing for system design interviews, it's important to be able to talk about all this independently. And most interviewers, I think, will be comfortable just going with the flow. So if they see you can comfortably talk about Kafka, they would go with Kafka. They would not ask this question. But because you asked it, we had to talk more about this. And for the record, I'm no expert in all these things. Like, honestly, I could have been wrong in some places. I just know in general what are they good for and what are they designed for. And Kane, are you with us?
Yeah. I was thinking at Redis. Redis is mostly because it wasn't built as a distributed system from scratch. Maybe they built around the same as Kafka, but Kafka was built as a distributed system, and Redis, distributed system, was added on top of it, kind of more iterative addition. And I mean, maybe it is mature enough. I just never had experience running it as your primary database. They market it the way as it could be now, but unless someone for example, Afir runs something like Jepsen on top of it, I would not trust it. And there's a good series of the blog posts they call it "Call Me Maybe" by Afir, and he's using his open source tool Jepsen. And as I remember, last time they tested it is in 2013. And I don't know, personally, anyone who, I don't personally have experience running it as a persistent database, and I don't know anyone who ran it so far. Things might change if someone runs Jepsen on top of it and proves it that it is consistent, it can withstand split brain conditions and stuff. Until that happens, I think people will be very, very cautious using it as a primary database. Even though, caveat, it might be ready, but no one proved it yet.
What do you mean by when you say? So, question for you: when you say prime,
talking.
Oh, a question for you. So, what do you mean use it as primary database? When we talked about Kafka, I wasn't considering Kafka being a primary database.
Okay, even if you use a queue, if you lose a queue, how you restore it? Then you have to have your additional database. Right,
yeah. So, I mean, it definitely has a persistent layer, right? Redis does, right? So, when I think about, using something like Redis over Kafka, it's okay, Redis is a very simple tool to use, right? I can, I can use it as a task queue, right? And
if it fits in the memory of one machine.
Right. Yeah. In this case, when I was thinking about, we had, 5,000 requests. We have 5,000 requests per second, right? I was thinking, well, that doesn't seem like a lot of data at first to
I think you missed this important part.
Okay, sorry.
5K per second, but when you start crawling from your seed, you keep adding more and more and more URLs to crawl. So your crawl queue would be growing by quite a bit.
Right.
it wouldn't just always be, if it's like 5K per second, it's not that you always have like 1 minute worth
Right.
of in your queue. You would have days worth of work in your queue.
Yeah. So is it, so maybe something that I didn't understand about Redis itself, that it's not distributed? Because I always thought that, you know, Redis was distributed. Okay.
It is. It could be distributed. There's Redis cluster, but I'm saying no one tested it, like how actually like how it behaves in the condition of the split brain. Like, can it persist the data? Can it, like, what is the data loss conditions? Like, as far as I know, like, there's not much work done in that space. Also, like, given like what you said, like Redis is really good if you need high read load. And in 5K per second, like Redis is like, really, why do you need Redis if any database can withstand actually like 5K reads per second?
Great.
And they are persistent. They created to be persistent. Like even any NoSQL, persistent NoSQL could serve. Like Redis is good when like your database cannot handle the load, so you cache, like it's usually in memory. But 5K per second is such a low number, so any like tested persistent NoSQL database can handle the load, and at the same time provide you like time tested like data loss safety.
That's
so
very
even
true.
if this was backwards, let's say like we had like 50, 100, like hundreds of thousands requests per second, then Redis would help. Like you had like hundreds of thousands reads, then we potentially would go into the Redis area and like maybe like even clustering, like have like multiple clusters of Redis. But with this condition, like Redis, I'm not saying like why you would add caching layer on top of it if your read rate is so low.
Right. That's a good point too. It's like, you know, these requests and perhaps just storing to database, you know, it'd be
really like your write rate would be probably high. Like in this case, like will be like almost like 1-to-1 ratio. So like I would be more worried about that, like to start with. Also, like
technically in this case we do have 1-to-1 ratio.
Yes, that's what I would be like more worried. Like Redis is good when you have like skewed to the read load ratio. So now like it's more like writing. Yeah.
Shall we explain more about this read to write ratio for people who are less familiar with the term?
I think like you covered it in previous sessions too. Like when you like read much more, like many more times than like, let's say like you read once, you write once, but you read multiple times, like X times. That would be your like read write ratio. In our case, it's 1-to-1. So like Redis is good when you have skewed read, like write read ratio, like when you have one write and it's like thousands of reads. But now we have 1-to-1. So I think like it's backwards problem. Like how do we write so much?
Actually, I think this is not a, I mean, it sounds true in theory, but I don't think it's true in practice, because since it's single-threaded, it's single-threaded, I think in the case of Redis, read is not much faster than write. If you want to read the same key a million times,
I'm saying like the persistent database writes, like we need to, like we don't need, like actually like we don't need to put cache, like Redis cache on top of something we have if it's 1-to-1. So because reads usually less expensive, and if we happen to cover writes in our persistent storage, then reads would be just like easy. Like writes, if it's 1-to-1 and we can handle the writes, I am 100% sure the reads would be served easily.
True. Well, yeah. In this case, I think what we're saying in different words is that if you need to optimize your database for reads, if you have a lot more reads than writes, then you need some external caching layers. So you can like you have a database that you run mutations through, and you have 5, 10, 100 read layers, so that all the read requests can be distributed across these readers. In which case, Redis is a great way to perform this read caching. It's like mem cache on steroids in this case. But in our case, the use case is the opposite. We don't need to read this queue from multiple machines. We just need each machine to read the next URLs to crawl once.
You know, like I usually start designing from like asking like very like dumb questions and like building very naive designs and see where they break. And let's say like if it starts with very naive design, we said like first of all we want the data locality. Like we don't want to fetch something like across the continents. Let's say like we have we start very simple. We have, let's say like the simplest way would be we start just a master slave system, like on top of like some relational database. Like I like Postgres. Like this is very simple. Like we have multiple like data centers in all, so like at all continents. Like so like for now, just one data center, and we just run there a replicated like Postgres instance. Like what's bad about it? Like as a storage, like what would happen? Like what is the problem with running it like this?
Are you asking the question to the group?
Yeah. Kind of I like asking like dumb questions to like simple solutions.
Yeah.
This is very simple solution. Like what's the problem?
Good point. Yeah, I love that approach a lot, because like I find myself often trying to use technology or just cater to the interviewer, to what he wants to hear, because often people want to hear, oh, a message queue in Kafka, right? But a lot of time, you know, we miss the important part of like, let's go with the simplest solution and then go up, right? And in this case, to answer your question, right, like one of the things to kind of mind is like, why even choose SQL in the first place, right? Like, do I need the transactional, right, capabilities, right? Is that a good? Do I need it? You know,
but why you don't?
Right. Like, you know, can I sacrifice some consistency, right?
Okay.
For eventual, and perhaps use like a NoSQL database where I can scale perhaps a bit easier, right?
Okay, that's a key point here. I think like stop here, and I think like that's the first obstacle kind of or meeting. The problem with traditional, say like we run the PostgreSQL replicated, is you can scale reads easily, but you cannot scale writes easily. Like it comes with burden. Like you can scale like manually cluster databases, but that's manual work. That's a lot of infrastructure work. And that's an overhead. So that's the first problem we're encountering. Like we cannot scale writes. It's like first, like, okay, we have like many URLs we have to write. Now like we are slowing down because we cannot write fast enough. And having this, like say like PostgreSQL setup already limits us. It's hard to scale. It's harder to scale than, let's say, like than the NoSQL promising us, where you can add a node and it does it for you, given you have the right schema. Okay, right. So that's the first point, like why we don't want this setup. Okay, now like go to the next point. I think like very important point here also. I don't know, like it's very important. I just want to like present it before you. It's kind of like a resource takeover and starvation, and what we used to call fair queuing. Let's say like you start crawling like Wikipedia, let's say, and it has like thousands of pages, and now like Wikipedia takes over your queue. Like nothing else can be processed until you finish with Wikipedia, for example. Just like taking over everything. And for like little guys, let's say it's bad because like Wikipedia probably like doesn't care because they're too big. It doesn't care if it's like crawled immediately. But it would be more fair if you try to distribute, kind of like try to crawl everyone, like kind of like trying to like give every domain its slice of time. It's like almost like in the CPUs. If you give like all time to your single thread, like all of the threads will be starved. And it's the same like with like crawler. If you crawl Wikipedia, like everyone else will starve.
Well, I think in our case, we did mention that there's going to be a component that pretty much is a distributed hash map that guarantees that no URL is crawled twice. And that's going to be the entry point to the queue. And I feel like if we go this route, we would take another whole conversation about how to make sure this queue is actually a priority queue, so that you can actually control the order in which it returns you the requests. Because honestly, you don't need this queue to be first in, first out for too many reasons. In the real crawling engine, you would have some policy that is also dynamically updated that tells you how soon should you recrawl the same URL. And you could have some heuristics. I think it's like the first heuristic would be to have it based on page rank. If the page is super popular, you probably want to recrawl it more frequently. If it's super unpopular, you don't need to put it on the head of the queue. So like even if you just insert these elements into the queue with a timestamp, there would already be a huge step forward. But I feel it's absolutely not the right use of our time right now to discuss these internals. I think what we really, really should focus on, and I think we're all going there, is Kane, imagine somebody asked, like, since you're obviously a lot more senior, imagine somebody asked you to interview the candidate on this question, and you didn't really prepare a lot on this. Based on what we just discussed right now, based on what Andy was talking about, do you think there's a correct answer as to which approach to use for like Kafka versus I don't know, Mongo versus RabbitMQ versus RAID classes and text files? Do you think there's any, like, obviously Redis would be a bad answer because the queue is just too large to fit in memory. But in terms of other answers, how do you think the better response should look like? How would you gauge it?
So you're saying, like, you're asking, like, what would be my preferred way? Like, what would be my preferred design for this?
Well, like, what would preferred design is a different question because if you and I were to design the system, we would talk on a different level. But if it's an interview setting, you just need to confirm the person qualifies for like mid-level or senior. What would you expect them to say so that you would say, oh yeah, it makes perfect sense. You certainly are at least a senior.
Okay, let me think a little bit about that. Well, first of all, I would expect asking the questions. You know, like every scale starts with identifying what breaks, what doesn't handle the load. Like, what is the place that doesn't handle it? And that's the first like step you do. Like, you identify the place, and like kind of we went into like a lot of places like without even thinking like what breaks and why it breaks first. And that's the first thing I expect a candidate to say. Analyze. Okay, we have, let's say like, and that's why I like starting with very simple tools because there's less places to break. Let's say like we just put like, that's why I mentioned the relational database. Everyone knows them, like everyone knows them. That's kind of like the common ground we can all talk about and identify like what does break first? Like what is that place we have to scale? And we can start talking, okay, that's probably like right because we said like it's 1-to-1, right ratio. That's what I would also expect for candidate to identify. And then like say like reads are a lot easier to maintain. So probably like the number of writes would kind of like break first. How do we solve that problem? How do we scale the writes? And from there, we can talk like about like different ways. Like that would be the first step to me. Like identify what breaks, scale this part. Next, like, okay, we're on like next level now. We scaled this part. What breaks next? And we like solve this issue one by one.
Yeah. Kane, I have a question for you. So, you know, we started that, you know, we have this, you know, we started with like, you know, we're pulling from this queue, right? We have this crawler component that, you know, makes a call and fetches the, you know, fetches the page, right? And then, you know, we have this component that, you know, that within the same, you know, the same fetcher can also parse. We agreed that the same, I guess, component or instance can parse that same that file, parse the URLs, right? Then after that, you know, I think somebody suggested you know, we should use I think Sergey suggested that we should do a message queue, right? And perhaps add those links over to the message queue, right? So I think I kind of missed of you know, I'm just playing devil's advocate here. Like I think I kind of miss like why we need that message queue and why we shouldn't I just go and use like, you know, straight to the database.
That's a very good question, and I would approach it this way. I would start building, like, as I said, again, from very simple tools, and then see, okay, it doesn't work, let's bring more tech. Because, you know, like as a rule of thumb, I like the notion, the less moving parts you have, the easier your design, probably like the easier it's to build and maintain. And it's pros and cons, and like you don't, it's kind of like more like a Occam's razor. Like don't bring entities until you need them. So in that way, you're thinking, right? And I support that thinking. Like use the razor of the Occam, like don't build unnecessary entities. Okay, and the way I would also like, I would support you. Let's say like we first identified that, let's say like relational database doesn't work because let's say I didn't say it doesn't work. I say like it's harder to work because the writes don't scale. Okay, let's say like we take some NoSQL, and we can like leave out the question what specific NoSQL it is. And let's say like we don't bring message queue yet. Let's say like we write directly to that NoSQL. We write, let's say like we write the list of the URLs we have to process. And now like, let's say like we have multiple workers talking to that database and pulling, let's say like tasks directly from the database and processing them. Like what's the problem we'll have to do ourselves? Like, first of all, it's not that we care too much that two workers process the same entry at the same time. It's not like financial transactions. It's like, it's really like, just like I don't want to waste like more resources than is needed. Like one processing is enough, but it's not critical. That's like one like axiom. But still, like I would like to prevent it. How do we prevent it? Let's say like one way we do, like we kind of like take ownership over it. Say like I'm working on it, no one else touch it. And kind of like then you can only pick from your database, from your NoSQL, let's say like something that means your database have to support at least indexes to pull the stuff that is not claimed by someone.
Right.
Okay, so you do that, and what happens if you die in the middle? Let's say like you claimed task and you died immediately. So now like you need some what is called like liveness state. Like you need to know that the consumer is live, and that's another like if you go into that route, I ask you a question, Andy, how do you solve this liveness problem?
Yeah.
Like,
so
as you suggested, like why do we need message queue? You suggested it, so I'm saying like I gave you like I went with you like halfway through, and this is the next problem we're hitting. Like solve it.
By the way, I can claim that your argument actually proves you do not need a message queue for the first implementation. That would be a big detour, because as you said, it's not financial transactions. If you can just
and I mean like at that point you decide it's like too much hassle. That's where we say, okay, we need message queue. Okay, like we kind of give up, but that's the way kind of like I approach it.
Yeah, because if you miss every 10,000, so every 1,000 URL to crawl, and if you recrawl another every 1,000 URL, the world doesn't break apart. It's a crawling engine after all. It's not financial transactions. So in this particular case, you don't need the first in, first out. You can just push the next URL to be crawled, do some random shard with some hash-based sharding, and you don't have the operation to claim the next URL to crawl. You have the operation to claim the next 500 URLs at random to be assigned to me. And if I lose them, no big deal.
Right.
Which is really important in terms of, it wasn't like, to be honest, in this 1.5 hours, I think this beginner's mind exercise of asking why multiple times was really useful, because I've seen it before in many interviews, including these meetups. People, like the last time we talked about eventually consistent replication of a database, and we just all agree on it should be eventually consistent because that's the term we use these days. Until Dorothy asked, do we even need it to be consistent at all? Like it doesn't really matter in this case, it's just a cache. So it's really good to ask these beginner's mind questions, since we can see our own biases. We don't have to design things based on the concepts we're familiar with. We really need to get to the root of that. And I think Kane is asking an awesome question here. Like, since I'm talking, let me moderate this a bit. I think in terms of covering the web crawler part, we did not get to design the component that deduplicates the URLs, which is actually important and interesting. It's like a big distributed hash map, which most likely is based on consistent hashing. I'm pretty sure we're going to cover this question as part of a different large-ish question. So I'll just make sure that on one of the next meetups, when we discuss some other large problems such as messaging or whatnot, I'll make an explicit note that, hey, this is, by the way, what you would do if you do need this large hash map for the tasks such as URL deduplication in the crawler. But I think we should be wrapping up slowly. We can stay for a bit longer after the official part is done. And I think for this last few minutes, let's recap on if we do use the message queue. If we do use the message queue, what are we left with? What should we do?
next
Are you
part,
asking?
next part, one thing that we pretty much missed is the storage parts. How are we going to store? How are we going to store this? Like once the messaging part covers the whole of like task distribution aspect of things on the crawling side. So now we need to think of like maybe how are we going to store these web pages?
Well, yeah.
Suppose
There's going to be
that
some distributed store in which we store the contents of those pages. Yes, that's I think the fifth component so far.
Mhm.
So again, I'll have to learn to do a better job at moderating this. I think in terms of having a good conversation and learning a lot, we've done a good job. We'll do better next time. So yeah, we did not cover the distributed hash map, and we did not cover the actual storage. Thanks for bringing this up. Yeah, we did not cover crawler traps. We did not cover if you need to extract URLs from other than the raw HTML body. Do you need to
Right.
JavaScript,
Yeah.
iframes?
Mhm.
Oh, also, like, question is, how much do you intend to build from scratch, and how much you can just like use existing tools? And are you building a cloud-centric design, or so like non-cloud-centric for some reason, like privacy? I don't know, like what other reasons could be. So
Yeah.
that kind of like brings the initial set of restrictions on what you could do.
If you have access to cloud like Redis, like Dynamo,
Yeah, like Dynamo or Bigtable or whatever. Yeah.
Bigtable is more relational. Google has PubSub too. But if you have access to large scale PubSub in the cloud, all your Kafka question is pretty much gone.
Yeah.
That's a good point.
So yeah, it would be very easy if we use something like GCP or AWS. Like there's no, like really, it will be a very easy exercise.
True. And Don?
Can I ask a question about the messaging, which kind of maybe I'm missing? So in the beginning, when we discussed like few approaches, one of them was message queue like Kafka, and another is message broker like Redis. And Kafka is not suitable because, if I understand right, it requires a complex orchestration, and which has a big overhead. And Redis is not also suitable because it stores everything on a single machine, so it doesn't satisfy the persistent requirement. Wait, what's left then? So like, which part are we actually missing? Okay, if this is not suitable and that is not suitable, what actually is suitable for that?
Well, so I don't think, first of all, I don't think it's encouraged in the interview to say that Redis is a message broker. Message broker is more likely Rabbit. We covered that too, but it's also unsuitable. Well, yes, Redis does not work. Kafka requires creative use cases with actually making sure you use it correctly and not get overloaded on the zookeeper level. That's where Andy asked a good question. Do we really need a queue? If we do need first in, first out, or some sort of priority queuing, you would either need to build something pretty heavy and complicated from scratch, or as Kane says, you would use some cloud provided queue, or you would need to build something else that is not the queue, but does the job of the queue. So that's actually, there was a reason behind me asking Kane a while ago, what would he assume to be the good answer to this question? I personally think that you gotta be really confident in your capacity to design systems to seriously suggest building a web crawler without the queue. I mean, most interviews would expect you to say, oh, so web crawling is like traversing the web graph, and web graph is tightly connected. And it's most certainly not a depth first search, it's a breadth first search. And BFS, unlike the DFS is recursion, it just goes down deep and deep. And BFS has this knowledge of how deep have we gone so far in each branch, so it slowly goes further and further. So it's certainly not a DFS, it's BFS, and BFS requires some kind of queue. So even if we now agree, it actually was a good session that we got this deep. Even though we now agree, you don't really need to use a queue, as in you don't need the retrieval from this data structure to be anyhow sequential. You can build a crawler based on randomly picking random URLs from different buckets and just push the different buckets as in high priority, low priority, medium priority, whatnot. This can totally be designed this way. I just think unless you really know what you're doing, if you're talking to somebody who wants you to design the web crawler and you do not even mentioned that you would rather use a queue for your crawl queue. It's even called crawl queue for a reason. Like, either you know exactly what you're doing and you explain exactly that you can do better than the queue-based solution would be, because as we just discussed today, queue-based solution on Kafka on some persistent queue would require you to be careful with zookeeper kind overhead and like not more than 5,000 partitions per topic. If you can explain all this, all the power to you. But in terms of, I still think the major part of the major goal of this meetup is to talk system design in the setting of making sure you are more confident explaining this in a setting that looks like an interview. And in this regard, I think even though Andy is perfectly right here, we don't necessarily have to use the queue. I still think it's a good way to think about crawling as the queue-based crawling.
Oh, of course, with that, like you could do it very easily if it was, say, like pops up, and you just do the say like the cloud functions triggered on the event from pops up, and it would be.
But pops up effectively is a queue.
It is a queue, and I'm saying like if we had it like the cloud centric, that's why like the queue and simple like on demand like triggering would solve all like majority of the problems of this problem.
And yeah, my biggest argument here, which I think would be probably along the line of the closing notes. My biggest argument here is that I think a good way to approach system design is really to think about A, talking to somebody whom you have to convince you know this, and B, always imagine that whoever's going to be implementing this is a lot less knowledgeable. So proposing the design that is easier to comprehend by today's standards, not today's tools and techniques, but today's standards of thinking along these lines, is always better. Because it shows you can explain yourself clearly. And today people know what pops up is. People know what a queue is. People know what Redis is. People know what Kafka is. So it would be strange to not bring this up, that, hey, I can do it using these primitive building blocks. They're not exactly designed for these purposes, and I'll have to work around some sharp corners. But unless I really want to implement something from scratch, which I will do better than the standard solution, because it will be tailored to my task, but it's going to be really freaking hard. And the idea of system design interview is to make sure that you can explain how can you solve hard problems using simple existing building blocks, which most people are familiar with. And if you're going to hire 10 juniors, there's a good chance that many of them would be able to manage Kafka and Redis and distributed queues. And there's a good chance that they would not be able to figure out how to implement consistent hashing-based distributed hash maps and literal elections, effectively re-implementing their own Kafka-esque, Kafka-style bus partitioning or whatnot. Making sense so far?
Yeah, definitely makes a lot of sense. And I just want to apologize. I know that, like, you know, I kind of deterred the group a little bit. I guess the reason why I was asking some of these questions is because I find myself like, I find that, like, you know, when talking about system design and kind of the resources that are out there on YouTube, it's like there's just this one magical solution that works, and you have to like memorize it, right? And you know, they throw out like, you know, Kafka and, you know, mess queues and all these types of like concepts, right? Without really, I feel like, going into why, you know, we're making these decisions, right? Versus a much simpler implementation that, you know, that could possibly have a breaking point. And you're right as well. Like, if in an interview, I would choose, you know, message queue route because that is something that, you know, interview wants to hear, and really you're kind of catering to the interview. But, you know, when I joined this, you know, I was hoping to get a more holistic kind of like overall conversations, you know, than just only tailoring to the interview process. And maybe I'm not sure if that was the intent of this. I'm not sure, maybe I missed the intention of the group meeting. And,
hey man, look, officially, while we're on the record, officially, I'd like to extend you a sincere thanks. I think in your style of questioning everything in an intelligent way is actually what we've been missing here. So I would be more than happy to have you for the next meetups with the same style. Don't be shy.
Okay, cool. Thank you.
Challenge me and others further. That's a really good way to not only go deep, but go deep into the pockets which are visible from the outside. Because oftentimes people like me, we see issues from the inside because we've done those things. And it's not exactly the topics which we should dive into. So you're helping everyone here.
Yeah.
Where should we dig? That's super helpful.
Yeah, I hope so. I just know that like I feel like I have a lot of friends who are great engineers, and I find that like a lot of like just memorization of what they hear is what they blur out, and and I can do the very same. I could go through. I feel like if I were to go through an interview process with a web crawler, I can tailor to what you want to hear.
Well, look, I do think that what we just covered would help everyone, including you, pass this particular question just in case. Look, on this note, I'm gonna thank you all. I'm gonna stop the recording.